Hey, welcome everyone to our Spanning Tree Protocol deep dive. I'm thrilled that you've chosen to join me for, I'm guessing, about 2 to 3 hours. Just a guess, just kind of set your expectations. But really important topic today. It's a big topic on both your CCNA exam and your ENCOR. That's the core exam for your CCNP Enterprise certification. And we're going to cover every topic that's on the blueprints for each of those exams. We might even go a little bit deeper than you need to know for those exams. So I am really excited to go through this content with you. We're going to do lots of demos. I'm going to get you engaged because I'm going to have you help me solve a spanning tree topology issue. You're going to be answering some questions. It's going to be interactive. So be sure and stick around for that. In fact, let's look at the agenda specifically. We're going to really break today down into 3 parts. The first part is the theory, and I think you're going to learn a lot in the theory, most of you will, of how spanning tree protocol works. We'll begin with the history of spanning tree. Why do we have it? What's it around for? We'll talk about different port states. We'll see how to identify the root bridge and the root ports and the designated ports and the blocking ports. We'll see that we can have a fairly complex topology that gives us redundancy but doesn't cause layer 2 topological loops, and we'll say why that is a bad thing. And we're going to go through together as a class, we're going to go through an STP exercise together. We're going to talk about how long it takes to converge if there is a failure. How long does it take to reroute and start forwarding frames again? And it might be longer than you would want, and we'll talk about how we can speed that up with some different parameters. Then we're going to take our first break after we go through that basic theory of spanning tree protocol. Then we're going to dive right into the configuration. We'll talk about CST or common spanning tree, Cisco's PVST plus, the theory, and we'll do a thorough demo. I'm actually going to be popping off camera from time to time to go swap some cables and observing the behavior of when I physically swap those cables. We'll talk about multiple spanning trees protocol, show you how to set that up. That's a topic on the ENCOR exam. And we'll talk about rapid PVST plus, where we can converge sometimes in a matter of milliseconds, and we're going to see how to set that up. And again, we'll take another Q&A break. And then in the third part of our session today, we're going to get into the bonus features, because at this point, we've learned what spanning tree is. Why do we need it? What is the theory of how it operates? We've gone into the configuration. Then we're going to see, how do we enhance it? How do we perhaps speed up that convergence time? We'll give you some different theories on doing that with approaches like port fast and uplink fast and backbone fast. We'll show you how to make your spanning tree topology more stable by protecting it against BPDUs, but with BPDU guard and BPDU filter. If we have some, just checking a couple of the comments coming in here, if we have somebody that maliciously attaches an Ethernet switch to the topology and they're wanting to sort of take over as the root bridge and start capturing your traffic, we'll show you how to prevent that. And sometimes there may be physical damage. I mean, there's a very nerve-wracking thing going on in front of my home right now as we speak. There are people out there with shovels digging very close to my fiber optic cable, which is how I'm communicating with you. So if I black out, there may be something going on up at the road, and I'm going to be checking on that really quickly. Always get nervous when we see shovels or backhoes around any sort of fiber optic cabling. But yep, that's going on right now during our big webcast. So we'll see how that pans out. And we'll take a look at how to protect us against somebody hitting it literally with a shovel and cutting one of the 2 strands in a fiber optic cable where we've got unidirectional traffic, but not bidirectional. That can cause some issues, and I'll show you how to overcome those issues. And then we're going to wrap it up with one final Q&A. So I cannot imagine what else we would talk about when it comes to spanning tree. And in some of these demos, we're not just going to say, here's how to set it up. Basically, we're going to say, oh, here's some extra stuff you can do as well. And when we do that, I think I already mentioned I'm going to be actually moving some cables around, and I'm going to have you guess as to what's going to happen when I do different things. So please have a notepad ready. Please be ready to take lots and lots of notes. And Yeah, hope you enjoy the session today. Cannot wait to get into it. Now, if you are new to our world and you don't know me, my name is Kevin Wallace. I've been doing this a long time. I've got a couple of CCAs, one in enterprise infrastructure and one in collaboration. I got my CCA back in 2001, so August 3rd, 2001. So I'm coming up on my 20-year anniversary. And I've been working with Cisco gear for over 3 decades, since 1989. I worked on the very first model of Cisco router, the old Cisco AGS Plus router. And I just love this stuff. I've been working with it literally for decades. And I taught courses for Cisco Learning Partners for about 14 years or so. And then back in 2014, I started my own training company, Kevin Wallace Training LLC. Been doing that for coming up on 7 years this year. Wow, time flies. I used to be a network designer down at Walt Disney World in Florida. My family and I, we are huge Disney fans, and I'll be telling you some Disney stories today as it relates to Spanning Tree Protocol, because that reminds me, when I was going for my technical interview at Walt Disney World, I was in a big boardroom where they had a big whiteboard up there, and they were asking me all these different technical questions. And one question they asked me, they drew up a spanning tree protocol topology, and they asked me to go identify which ports were blocking. And I thought I understood spanning tree really well at the time, and I missed it. I got the job, fortunately, but I missed that spanning tree question. Oh, that killed me. But you're going to learn today what I did not know then, so you would not miss a similar question or not do it wrong in the real world. I've written a bunch of books, done a lot of video courses for Cisco Press and Pearson IT certification. I was honored to be a distinguished speaker at a couple of the Cisco Live conventions back when we could actually go and attend those in person. I cannot wait to start doing that again. It's been virtual for the last couple of years. But yeah, bottom line is I love this stuff, and I cannot wait to get into it. So let's jump into our very first topic, which is an introduction to Spanning Tree Protocol. And we got to go way back. I mean, we got to way back like to the 1980s in order to do this. Because back in those days, there were no Ethernet switches. We had Ethernet bridges. Now, a bridge logically works about like a switch does. A bridge is going to learn what MAC addresses live off of its ports, and it's going to build a MAC address table, and it's going to make forwarding decisions based on where that destination MAC address lives. Sounds a lot like a switch. However, the bridge does it in software. Now, today's switches, they've got these super fast ASICs, these application-specific interface controllers or integrated controllers, and yeah, they're going to make decisions just super, super quick. But a bridge was a lot slower. And yeah, they didn't have many ports, but this was the genesis, really, of Ethernet switches. But the reason I bring this up is we still use the term bridge when we're talking spanning tree protocol. We'll talk about the root bridge a lot, and we'll talk about bridge protocol data units. I want you to know why we're using that term bridge. It goes way back to the 1980s when Radio Perlman was working at Digital Equipment Corporation. She was working at DEC, and she was wanting to come up with a way to have a redundant connection between these Ethernet bridges and still not cause some problems that accompany a layer 2 topological loop. We'll take a look at it in just a second, because some really ugly things can happen if we have a loop. Packets can just start circulating forever. And she came out with the very first version of Spanning Tree Protocol. When I was configuring that original Cisco router back in 1989, I remember I could set that thing up to run either the DEC protocol, the DEC version of Spanning Tree Protocol that Radio Perlman came out with, or I could select I guess it was around 1990 then, because in 1990 I could select 802.1d. That was the IEEE flavor of a Spanning Tree Protocol that they introduced. Now, by the way, we're going to talk later about, for your notes, something called Common Spanning Tree, or CST. These are that. The original DEC version and 802.1d, those are going to be common spanning tree protocols. And we'll define what that means later, but just might want to make a note that when I talk about a CST, probably talking about one of those two implementations. But today, we don't use bridges, we use switches. Logically, the operation's the same. We learn what MAC address lives off which ports, and we make forwarding decisions based on those destination MAC addresses. And the reason that this is such a big deal, because, I mean, look at the switches I've got on screen, A, B, C. If one link goes down, you see that there's a path from any one switch to any other one switch. Because what we're trying to do here is we're trying to construct a loop-free topology logically. Why it's called a spanning tree, it reminds us of a tree. I took this picture of a tree. This is in my backyard. And if you'll, now I know there are some rare trees that actually have one branch loop back on itself. We're not talking about that. Most trees that I've seen, they sort of just go up and branch out and out and out and out. You do not have one limb branching back in and touching another limb. It's a loop-free topology, and we're going to be building a loop-free topology throughout our switched network today. And the reason is switching works different than routing. We don't have this issue with routing. Take a look at that top topology where I've got a couple of routers. Let's say something happens, and we are now in a layer 2 topological loop. That's fine with routing because in the header of an IP packet, there's a field called the time to live field, the TTL field. And it's basically a timeout. Every time we go through a router, that TTL field gets decremented by 1. So on screen, it went from a 2 to a 1. And when it reaches a 0, it timed out and it's discarded. So we don't have this infinite looping of packets at layer 3. But down at layer 2, that's where we have an issue. Down at layer 2, there is no time to live value in the header of a frame. So if we get a broadcast frame going, for example, it's just going to circulate endlessly. It creates what's called a broadcast storm. And in addition to that, it can cause MAC address table corruption because you send out a broadcast, it goes into these switches, they start sending traffic to one another, and this switch says, oh, this frame coming from the always MAC address, I just learned it on my top interface, now I'm seeing it on my bottom interface. Let me update my MAC address table. And then when it loops around, it does it again. Let me update it again. We've got an unstable MAC address table, and we have a broadcast storm that can literally bring a network to its knees. True story from my days down at Disney. I remember a huge spanning tree protocol issue we had. It was over around Epcot. If you've ever been to Walt Disney World, I remember it was about 3 p.m. one afternoon, and we get the call that guests over at the Yacht and Beach Club, that's one of the resorts, or a couple of the resorts next to Epcot, they were not able to check in guests. And that's like prime time for checking in around 3 p.m. You see, back in those days, that we had these little, these key to the world cards like this. This card was how you got into your room. It's how you purchased merchandise. It was how you got into the park. It's how you got food. It's pretty critical you had this card. Nowadays, they have what are called magic bands, and now they're changing it to an app on the phone. But back in those days, you had these key to the world cards with a magnetic strip on the back, and we couldn't make them. And the reason is there was a network issue. So we hop in the company van, we rush over to Epcot, and right near the big Epcot ball, what they're remodeling it now, but it used to be called Future World. A lot of people don't realize that there is a partial tunnel system under Epcot. Now, lots of people know about the Utilidors under the Magic Kingdom, but there's actually a partial tunnel system under Epcot. So we went down 3 floors, and that's where all the equipment was. It was we had some Cisco Catalyst switches in there, and we had our packet capture device, and we started capturing packets. And it was evident fairly quickly that we had a broadcast storm. We had redundant links going out to these resorts, which is great. We want redundancy if something fails. But that supervisor engine in that Cisco Catalyst switch, the spanning tree process, for whatever reason, just stopped. It wasn't doing its job. So we had a broadcast storm. And when you have a broadcast storm, it can consume resources on PCs on that network, literally to the point where you cannot move your mouse pointer around because your PC is so consumed with taking a look at all of those broadcasts and saying, oh, that's not for me, discard. That's not for me, discard. And it was kind of a disaster. You had all these guests just roaming around the lobby of the Yacht and Beach Club. Those are some of the more expensive resorts there. So that was kind of a problem. We had 2 choices. Number one, we realized that we have a faulty supervisor engine. It was a modular switch, so we could make a backup of the config, run across the property in our van to get a replacement part, come back, put the new part in, upload that config that we made a copy of, plug it all in. That would probably have taken about 45 minutes. That's a lot of downtime. You know what we did instead? Those two redundant fiber links going into the supervisor engine, we just yanked one of them out, and then everything started working. Here was the logic. It's better to have a non-redundant yet functional network than a redundant and not functional network. So just by physically breaking the loop, yeah, that killed the broadcast storm. Now, somebody came back late that night to minimize impact on the users. That's a big deal. And they fixed it at that point. But yeah, personal history of how I know that a broadcast storm can just destroy your network. Now, let's talk about how all this works. The first thing I want us to do is answer 4 questions. You might want to, you do want to jot these 4 questions down in your notes. When you're analyzing a spanning tree topology, you want to answer these 4 questions. And we're going to go through them nice and slow, one at a time, and then I'm going to challenge you to do it. So pay careful attention. Question number 1, now this is a simple topology here. I've got a more complex topology I'm going to challenge you with. But in this very simple topology, question number 1, who is the root bridge? Just like that tree I showed you earlier. All the branches are sort of pointing back down to the root. All the nutrients are flowing out of the root. It's sort of the central point of the tree. Same thing with our spanning tree. All of our data flow points back towards, now it's not all the traffic's not necessarily going through the root bridge. Notice we're still using the term bridge, but it's that central point that we're sort of pointing back to. We don't want to let spanning tree just happen because it will. I remember one time I was interconnecting 3 Cisco switches, and this is back in the early 2000s. At that time, like the ultimate Cisco switch was the old Cisco Catalyst 6500 series switch, and I had a 6509. That's my favorite piece of Cisco equipment of all time, by the way. I call it the box that rocks. But I had this super powerful 6509, and then I had sort of a mid-tier 3000 series Cisco Catalyst switch. And chat it in if you remember this one. Does anybody remember the Catalyst 1900 series switch? We're going way back in time here. It had 10 megabit per second ports on the front of that switch. It was a slow switch. Cisco bought this company called Grand Junction, and they inherited it from them. But bottom line is, I plugged these 3 switches in. It was like, I started to say good, better, and best, but it was like bad, okay, and awesome, I guess would be the 3 rankings. And guess who the root bridge was, if I didn't do anything? Yeah, that older than dirt Catalyst 1900 series switch became the root bridge. We don't want that. We want to strategically decide who's going to be the root bridge. In fact, when I was working at Disney, one of the big things I did there was design networks, and I had to go before a review board and explain how spanning tree was going to work and why I chose this as the root, how I was doing redundancy. So there's a lot of thought that goes into this. Don't let spanning tree just happen. I want you to pick the appropriate route for each particular VLAN. So question number 1 we're going to answer is, who is the root bridge? Who is that central point that we're pointing back to? Next, we're going to identify the root ports, and I'll define that for you. We're going to see who the designated ports are. I'll define that. And which ports are blocking. Now, here's the question that I missed on my interview. They gave me a topology. It was much more complicated than what we see here. They said, go to the board and mark which ports are blocking. Now, I thought I understood spanning tree at that time. I had my CCNP at that time, and I went up to the board and I thought, I got this. Yeah, here's the root bridge, and we're forwarding here, and we're forwarding here. Yeah, we're not sending traffic across this link. Just like in this example, we're going to see that we're not sending traffic across the bottom link. But here was my false assumption. I don't want you to have this. There was no data, no user data going across a particular link. So I said both sides were blocking. I thought if we're not sending user data, they must both be blocking. And that was wrong. You will never, ever have a link in a spanning tree topology where both sides are in the blocking state. It only takes one side to be blocking, not to be communicating user data. So that's how I missed the question. We're going to see that every single segment in your topology, I don't care if it's carrying user data or not, every single segment has one and only one designated port, and we'll identify that. Everybody else, assuming they're administratively up, those are your blocking ports. Or sometimes we say that those are our non-designated ports. So let's analyze this basic topology, and then I'm going to challenge you with a little bit more complex topology. But question number one is, who is the root bridge? Now, the root bridge is going to be determined, now please take some notes on this. The root bridge is going to be determined by the Ethernet switch that has the lowest bridge ID. Now, what is the bridge ID? It's made up of two different parts. It's made up of the bridge priority, which we can influence, and the bridge's MAC address, which is burned in to that MAC address, or burned into that switch at the time of manufacture. But the first thing we consider is the priority. And on Cisco Catalyst switches, if we don't mess with the priority, we just take the default value, that value is 32,768. And that's what all these are set to on screen. If all those are a tie, we go to the tiebreaker. The tiebreaker is the MAC address. And we're looking for the lowest bridge priority. So whoever has the lowest MAC address, they become the root. So in this case, you tell me. Chat in SW1, 2, or 3. Just put it in your chat and tell me, who do you think the root bridge is in this very basic topology? Is it switch 1, switch 2, switch 3? I'm showing you the priorities and the MAC addresses on screen for all switches. Now, there's like a 15-second delay from the time I ask it to the time you hear it. So I'm killing some time right now for you to hear my question and respond. We've already got a bunch of responses coming in. You know, we've got... we got Chino and looks like I remember Georgia. Georgia's answering correctly, of course. Marcos, Chris, Kenny. Yeah, on and on and on. And by the way, we're on different platforms today, so if I don't see your question, it's we're bouncing around. But Miriam's keeping an eye on all that stuff in the background. But yeah, I don't know if I saw anybody with the wrong answer. It's switch 1. And that's because we've got a tie when it comes to the bridge priority, and we look at the MAC address, and the all 1's MAC address on switch 1, that's lower than the all 2's MAC address, the all 3's MAC address. So we can say, yep, switch 1, that is our root bridge. Next up, who are the root ports? Now, a root port, hear me on this, a root port is the one and only one port on, and here's the big point, a non-root bridge. That's closest to the root in terms of cost. Let me break that down for you. It's on a non-root bridge. So the root bridge itself, SW1 in our case, has 0 root ports. These are on non-root bridges. And there's only one on all those non-root bridges. And it's the port that's closest to the root in terms of cost. Well, what do we mean by cost? Cost is a function of link speed. And this has actually changed over the years a bit. Here are the numbers I would want you to know going into an exam environment. I would want you to know the traditional way of doing this primarily. When I started working with spanning tree, and this is still the default on most of our switches today, it was what's called the short path cost method. If you had a 10 gig link, not 10 gig, a 10 meg link, going back to those old 1900s, you had a port cost of 100. Okay? If you had a 100 meg link, your cost was 19. That seems a bit random. I don't see any kind of linear relationship there. If you've got a gig port, and by the way, all the ports on screen right now are gig ports, that was a cost of 4. Or a 10 gig port, that's a cost of 2. Do you see that this doesn't have any future proofing built in? Because today in data centers, it's not uncommon to have 40 gig links. Or we could have, there are even some transceivers out there that give us a whopping 400 gigabits per second. And we're already down to number 2. How do I distinguish between a 40 gig link and a 400 gig link? yeah, we need a different way of assigning these costs, don't we? So we're going to say that we need to use a different method. Instead of the short path cost method, in the future, we're going to be using more frequent, and we should set this up on all of our switches, but we should use what's called the long path cost method. Now, this is a linear relationship. All you have to know is this formula. You take 20 terabits per second and you divide by the port speed. That's it. So let's say you've got a 10 gig port. What is 20 terabits? In other words, what is 20,000 gig divided by 10 gig? 2,000. That's how easy it is to figure it up. Now, I'm going to stick with the default in today's demos. I think that's more likely what you would be faced with on the exam and probably in any of your customer sites in the real world. But in the future, if you're installing a new topology and you can control all the switches from the beginning, I'd want to go with the long pass cost method because that's got some future proofing. So let's take a look at some of the port costs. First of all, on switch SW2, the distance from the root, if I went directly up to the root over that gig 1/0 port directly up to the root, that would be a cost of 4 because it's a gig link. But I could go over to switch 3, that's a cost of 4 just to get there, then go up to switch 1, that's another cost of 4. So grand total, that would be a cost of 8 if I were to go in that direction. But same thing for switch 3. It's a cost of 4 if I go directly, but if I go to the other ones and come back up, that's a cost of 8. So for each of the switches, we're going to say which port is closest to the root in terms of cost. Well, on switch 2, a cost of 4 beats a cost of 8. So I'm going to go with gig 0/1 on switch 2. Same thing on switch 3. I'm going to go with gig 0/1. So we now have answered 2 questions. Who is the root port? And, or actually, who is the root bridge is the first question, and then who are the root ports? The next question we ask is, who are the designated ports? And I made a big emphasis on this one earlier. I said that every link, I don't care if it's carrying user data right now or not, but every single link has one, and only one, designated port. And it's the port on that link, or which end of the link is closest to the root in terms of cost. So let's put ourselves in the mindset of that bottom link right there between switch SW2 and SW3. Actually, before we do that, we've got a couple links coming out of the root bridge. You know what? We don't get closer to the root than being on the root, do we? So we get to take a shortcut here. Every link coming into the root bridge, just by definition, those are designated ports because you're not closer to the root than being plugged into the root. So that's an easy one. The only link that's not plugged into the root is that link between switches 2 and 3. And we're going to ask, who's closest to the root? Let's put ourselves on the SW2 side of that. What is its distance from the root? Well, if I left from SW2, we said that's a cost of 4. Okay, what's my cost on the SW3 side? Well, going directly up to switch 1, that's also a cost of 4. We got a tie. What do we do in the case of a tie like this? Well, we look at who's on each end of this link, and we ask, who has the lowest bid? Who has the lowest bridge ID on this bottom link? And the priorities are the same, so we say, who has the lowest MAC address? SW2 has a lower MAC address than SW3. So we're going to say on that bottom link, SW2, that's going to be our designated port. And finally, we're asking who's left. Now, assuming we're not administratively shut down, if we're administratively up, everybody that's left after answering who's the root bridge, who are the root ports, who are the designated ports, the only ports that are left are blocking. This is what I did not know how to do in that interview for Disney back in the day. And yeah, I thought both ends were blocking. I did not understand what I've just really emphasized to you, and that is every link, even if it's not carrying user data, contains a designated port. All right, I want to challenge you. Are you ready? Got your thinking caps on? Let's take a look at a little bit more complex topology. I'll give you a moment to just soak it in. Most of the links are gig links. Notice up top between switches A and B, it says TE 1/0/1 and or it says that on both of them. TE means 10 gig. Remember the cost of a 10 gig link using that short path cost method was 2. So a gig link, you'll need these numbers for this exercise. The cost of a gig link is 4. The cost of a 10 gig link is 2. And I've shown you the priorities on screen for each switch, and I've shown you their MAC addresses. My question to you, chat it in. Who's the root bridge? That's question number 1. And I'll try to look at, we're on YouTube and Facebook and LinkedIn and people on our website. So go ahead and chat it in. I'll try to check some of the different interfaces and see how we're doing. So tell me, if you would, who is the root bridge? Who is the root bridge? Looks like almost, I'm not sure I've seen any. Oh yeah, I saw 1 or 2 incorrect answers. Most people are getting it correct. Most people are noticing that switches A and B, they have a lower priority. Their priority is 16 through 84. That's lower than the default of 32.768. So it's going to be either A or B, but then we've got to go to the tiebreaker between them. Who has the lowest MAC address? Well, let's look at the first 3 hexadecimal digits in that MAC address. On switch A, we've got 000. On switch B, we've got 001. Yeah, 000, that's less than 001. So we're going to say that switch A is going to be, that's going to be our root bridge. Next up, let's ask, who are the root ports? I'll do the, actually, let me have you do this one. On switch B, B as in boy, tell me, which port is my root port? Is it TE1/0/1, gig 1/0/7, or gig 1/0/5? Just chat it in. Who do you think my root port is? What do you think? Oh yeah. Most people are all over this one. They realize that 10 gig link, if we used it, it would have a cost of 2. If I used 1/0/7, it would be a cost of 4 just to get down to switch C, and then it would be another cost of 4 to get from switch C up to the root. So that's 4 plus 4, that's 8. If I went from switch B down to switch D, as in Delta, that's a cost of 4. And then from D up to A, that's a gig link, that's another cost of 4, cost of 8. Yeah, clearly, the 10 gig 1/0/1, that's my root port on switch B. And by the same logic, on switch D, it's a cost of 4 if I go directly to switch A, but it's a cost of 6 if I go up to switch B, that's a cost of 4, and then go across to switch A, which adds on a cost of 2. 4 is less than 6, so my root port on switch D is going to be gig 1/0/1. Now, on switch C, this is where it gets tricky. Pay careful attention here. There are 3 ways of getting to the root. Gig 1/0/10 and gig 1/0/11, they've got direct connections up to switch A, the root. And they would each have a cost of 4. Now, I'm pretty sure that my root port is not going to be gig 1/0/2 because that's going to use a cost of 4 to get over to B and another cost of 2 to get over to A. That's 6. So it's out of the game. But the question is, and I'm going to ask this before explaining it to you, because here's what I've noticed after teaching this for decades. Many people, I've had many students that think they know how to do the tiebreaker here, and they misunderstand the rule. So I'm not doing this to make you feel bad about yourself. I want you to struggle with this one. I want you to miss it now rather than missing it in the real world or on an exam. So my question to you is, on switch C, which port is my root port? Because it looks like a tie. The cost is the same. It's a tie. So tell me, if you would, is it gig 1? In fact, you can just type in 10 or 11. Is it gig 1/0/10 or 1/0/11? And tell me why you're saying that. What's your logic? What is your logic? I'm seeing lots of 10s and lots of 11s come in here. All right, let's go through it together. Yeah, most of you you're on the right track. And some of you just know the rule, and my hat's off to you, because most people don't get this, or a lot of my students don't get this coming into this training. But here's the deal. A lot of people have heard that, the first tiebreaker, by the way, that is, well, let's look at the switch on the other end of each link, and whichever switch has the lowest bid, that's the root port we'll use going to that switch. But here, they're connected into the same switch. It's a tie because switch A is the end of both links. So the bid is going to be the same for both links. Now, the next tiebreaker that we can look to is, let's look at the port. We'll get into the difference between port number and port priority a little bit later. But for now, let's say it's a tie when we're looking at the bid on the far end. Now, many people have heard, okay, if that's a tie, then I'm going to go with the lowest port number. And that's true. Now, I've had many students tell me that when I ask that question. They'll say, it's the lowest number, so I'm going to go with 1/0/10. They understand it's the lowest number. Great that they understand that. But it's not the local port you're examining. You're looking at the far end of these links. You'll know the spanning tree with bridge protocol data units, it will tell you the port ID and the port priority of the port on the other end of the link. That's the reason I crossed those links. Got a little sneaky on you there. But we have to look at the far end. We have to look at switch A. And on switch A, 13 is less than 14. And on switch A, gig 1/0/13, that connects to gig 1/0/11 on switch C. So it's actually gig 1/0/11 that's our root port. That was a tough one. And again, no worries at all if you missed that. We have tons of students that always miss that because it's not super obvious. And I'm actually going to prove that today to you. I'm going to physically swap cables on the topology I have here in the little server room behind my studio, and we'll see it happen. So I'll prove to you that that's not just theory, that we're going to watch it happen. So we've answered the first two questions. Who is the root bridge? You guys nail that. We said, who are the root ports? We got through that. Now we're saying, who are the designated ports? And remember, every single segment has one and only one designated port, and it's the port on that link that's closest to the root in terms of cost. And we get to start off with the big shortcut, because we said you don't get closer to the root than being on the root, which is switch A. So all of those links going into switch A, ding, 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 we get to write those down just instantly. Those are all designated ports. That only leaves us with like a couple more links. There's the link between C and B, and there's the link between D and B. Okay, let's take a look at that link between C and D. And we say, which end is closest to the root? Well, from the switch C perspective, it's a cost of 4. It's got a gig link going up to the root. From switch's B perspective, it's got a cost of 2 over that 10 gig link. So yeah, I'm going to go with the switch B side of that. That's going to be my designated port. And by the same logic, between the switches B as in beta and D as in delta, we're going to have a cost of 2 on switch B, but a cost of 4 on switch D. Yeah, again, I'm going to go switch B. And now we say, assuming all these ports are administratively up, we say who's left? Those are our blocking ports. Everybody else is blocking. This is what you do in your design. This is the kind of thing I would have to draw up on the board as I was going before a design review. Okay, here's the topology. Here are the different port states. Here's why I selected this as the root bridge. And a couple of reasons you might want to select one root bridge over another. One reason is the processing power of your switch. It's going to be handling proportionately more traffic than some of the other switches. So let's make sure it's a higher end switch. It's a little bit more, the processor's more robust, we'll say. And we're going to hopefully choose that one. But we also, as a second criterion, we need to look at traffic flows. What does the traffic flow look like on VLAN 100 as an example? Does most of our traffic go over to this data center? Does most of our traffic go to the internet? Does most of our traffic go over to this R&D department? look at your traffic patterns, and based on your traffic patterns, different VLANs might benefit from different spanning trees, different topologies, different root bridges. And I'm going to show you today how you can assign different root bridges to different spanning trees. And I wanted to show you, I kind of highlighted it in blue for you. This is the resulting spanning tree that we have. We've got everybody pointing directly back to switch A as it turned out. But the beautiful thing is, I sort of ghosted out the red links there. If one of those links were to fail, one of the blue links, we've got a backup path. That's the beauty of spanning tree. We're not forwarding user data over any of those ghosted out red links, because that could cause a broadcast storm and MAC address table corruption. We're only forwarding user data over those blue links. Just like that tree in nature that I showed you earlier, we have a loop-free topology pointing back to the switch that we have selected as our root bridge. But if one of those blue links were to fail and we had to select one of those backup links, a big question is, how long does that take? Let's consider that before we take our first Q&A break. I'm going to talk about traditional spanning tree first, and then later on today, we're going to see how to speed that process up a bit. But let's for now just talk about traditional spanning tree. Let's say that we've got this topology, and there is if I'm on switch 3, I'm sending traffic from switch 3 up to switch 1, going out of gig 0/1, like we talked about earlier. But let's say, what I'm hoping is not going to happen in my front yard where they're digging really close to my fiber right now. Hopefully we don't sever that link somehow, and that breaks. Now, when that breaks, the great thing is there's still a way for switch 3 to get to the root. It just has to go out gig 0/2. Now, that's currently blocking. The question is, how long does it take to go from blocking to forwarding? It's not instant. You see, what's going to happen is, in fact, let's back up. How does switch 3 know that it's still in communication with switch 1? Well, every 2 seconds by default, that's called the hello time. By default, every 2 seconds, switch 1 is sending out a frame called a BPDU. And by the way, those go over links that are not even forwarding data. But a bridge protocol data unit, that is going to say, for one thing, it's like, hey, I'm still here, I'm still alive. Here's my bridge priority, proving that I still am the best switch for the job. I've got the lowest bid. But it's not that uncommon. I mean, it's not unheard of that we might drop the occasional packet. So we don't make the assumption that switch 1 is down immediately. We give it some time. We're going to wait for 20 seconds. We're very patient. We're going to wait for 20 seconds until, just in the hopes that a bridge protocol data unit is going to show up on gig 0/1. But after 20 seconds of crickets, we're starting to suspect something is up, folks. We need to start transitioning my blocking port to a forwarding port. But we don't do that immediately. We say, all right, let's go into our next state, and that is the listening state. Now, in the listening state, please take notes on this. I was watching somebody teach this earlier this week. I was looking at one of their videos, and they described it incorrectly. So I want to make sure you get it. I want to make sure you get it right. In the listening state, number one, we're not sending user data right now. We're not populating our MAC address table, which is what I heard somebody else say to their students. We're not populating the MAC address table. We're listening to BPDUs. We're trying to learn our place in the network. We realize there's been some change in the topology, and we want to see what our role is. I mean, who knows? Maybe we're the root bridge after this change. But we're just kind of listening on all of our ports to BPDUs, trying to figure out which port do I need to transition to forwarding? Am I the root? Who is going to be the root? We do that for 15 seconds. And then once we determine, okay, I'm going to be listening for 15 seconds, and I've determined that, yeah, I'm probably going to start forwarding out of gig 0/2, but I don't do that immediately either. I wait for another 15 seconds, and that is in the learning state. In the learning state, I'm going to say, I'm convinced I'm going to be using this port. Now I'm going to start listening for MAC addresses showing up on all my other ports. So if I need to send traffic to that destination MAC address, I know what port it lives on. So I spend 15 seconds populating my MAC address table. And then finally, after a total of 50 seconds, I'm forwarding. But again, it took 50 seconds to get there. It was 20 seconds in blocking, 15 seconds in listening, 15 seconds in learning. That can be a long time. That can be a long time before we reconverge. We'll talk about how we could speed that up a bit today. By the way, here's another misconception I want to make sure that we get straight while I'm thinking about it. Talking about convergence times. Has this ever happened to you? It's happened to me. I've gone up, I was working in a server room one time and I had a laptop with me with an Ethernet connection and I plugged into like a switch port and my PC or my laptop, I think it might have had one of those SSDs, so it booted up really quickly. Almost like an instant on kind of a thing. So it just boots up and it gives me an error message because it had tried to go out and get an IP address or find a server or something. It tried to look at something on the network that it couldn't see, so it gave me an error. The reason it couldn't see it is the switch port into which I had connected was still going through its spanning tree delay. Now, here's my question. I didn't tell you the answer to this. I want to see if you can logically figure it out. I want you to struggle with this so you're going to remember it later. My question is, and put it in the chat if you would. If I plug a PC into here's the key, an unused switch port, it's empty. It's up, but it's empty. I plug it into an unused switch port and I turn it on. How many seconds is it going to take for that unused switch port to transition to forwarding if I've got spanning tree enabled on that switch port? How many seconds is that going to be? Go ahead and chat that in if you would. Wow. I am shocked to see so many correct answers, but I'm thrilled I'm seeing so many correct answers. Yeah, it's going to be 30 seconds. The reason is that port had not previously been receiving bridge protocol data units, so it's not missing them. It's not going to wait 20 seconds to receive bridge protocol data units because it was not receiving them before, but it still has to go through the listening and the learning state. Well, 30 seconds is too long when we're plugging in a PC, and congratulations, we've just got an amazing number of people that got that right. I'm blown away by how many people got that correct, but awesome job. I'll show you today how to speed that up to on the order of maybe less than just a few milliseconds, less than a second. Now, we've kind of covered the main theory right now of spanning tree. We're about to dive in here in just a few moments into some configuration, and we're going to be expanding on what we talked about. I'm going to be physically swapping some cables around. We're going to be changing the port priorities to influence some stuff. We're going to be predicting what's going to happen, and we're going to check it out, and we're going to be forcing a bridge to be a root bridge and a secondary bridge. We're going to configure like 3 different versions of spanning tree. This is kind of maybe the best part of the course if you get into configuration like I do. Hey, welcome back from that break, everyone, and we're ready to jump into some configuration now. Let's first understand what we're trying to improve upon. Remember, we talked earlier on today about 2 different flavors of common spanning tree. We said Radio Perlman's original DEC implementation and the original IEEE 802.1d implementation. We call those CSTs, or common spanning trees. And here's what that means. With a common spanning tree, which again is the .1d standard, every VLAN in our topology uses the same spanning tree, because typically when you've got a bunch of switches in an enterprise interconnected, number one, they're probably interconnected with trunk connections. And number 2, there are probably multiple VLANs flowing over those trunks, and different VLANs benefit from having different topologies. VLAN 100, as I mentioned earlier, maybe it benefits from switch 1 being the root. Another VLAN benefits from switch 2 being the root. But with common spanning tree, or 802.1d, the original version, it didn't matter. Every VLAN was stuck using the same tree. So you probably had some suboptimal paths. Then Cisco came along with something called per VLAN spanning tree, or PVST. And with per VLAN spanning tree, Cisco said, Oh, by the way, I should probably distinguish between a couple of terms you're going to see in the literature. You may see this written as PVST, per VLAN spanning tree, or you may see it written as PVST plus. With PVST plus, and by the way, I'm fine if you want to use those terms interchangeably. Even the Cisco syntax, the commands, they use it interchangeably. But technically, if you just want to know the difference, if you get confused, the plus means that the link interconnecting our switch is running .1Q trunk encapsulation. That's it. That's the difference between the plus and the not plus, but I'm fine if you want to use those terms interchangeably. But the beauty of PVST or PVST plus, and I'll use those terms interchangeably as well. By the way, in this topology that I've got on screen, I've got .1Q trunks running, so we're going to be setting up PVST plus. But the big benefit is we can assign different switches to be the root for different VLANs. On these switches that I have, and by the way, I've got this topology right now in my live topology. It's in a server room just behind me. I'm going to be running back there and swapping some cables in a few moments. But I've got the default VLAN of 1, and I created VLANs 100, 200, 300, 400. Yeah, let's see how we might have different VLANs. Well, let's make each VLAN use its own instance of spanning tree to begin with. Now, before I go out to the live topology, if you can read, by the way, I didn't put the priorities on here. I'm going to be changing those a little bit during the demo. I thought it wouldn't be a good idea to have them on here for that reason. But right now, the priorities are at the default. They're all 32.768. So tell me, if you would, chat it in. Which of these switches is the root bridge right now? Is it switch 1, 2, or 3? What do you think? Just checking to see what people are chatting in. A lot of votes for switch 2, I'm seeing. Anybody else? Yep. It looks overwhelmingly like, I'm not sure I've seen anybody type in anything other than switch 2. You guys and gals are rocking it today. Awesome job. I think you're right, but let's go prove it. I mean, it's one thing to do it in theory. It's another thing to actually do it in practice. So let's go out, and I'll take my face off the screen so we can see this a little bit larger, and I'll put that topology in the upper right-hand corner where you can reference it. Now, you told me that switch 2 was the root. Let's just kind of tour around and see what's happening on each of our 3 switches. Right now, I'm on switch SW1, and I can say show spanning -tree. Now, if I just pressed enter right now, it would give me a lot of output. It would give me the spanning tree configuration for VLAN 1, for VLAN 100, 200, 300, 400. Just to keep the output simple right now, I'm going to say just show me this for VLAN 100. And it says, all right, for VLAN 100, our root ID, in other words, that's the ID of the root bridge. They have a MAC address of this. Just looking, yeah, that does appear to be switch 2. Good job. And we're saying this is their priority. Here's my MAC address, and here's my priority. Oh, and you might see something here that's a bit confusing. You might say, hold on, I thought Kevin told us that the default priority was 32.768. That says 32.769. That's a side effect of using PVST because Cisco doesn't want any 2 VLANs to have identical priorities. So what they do is that they take the priority value and they add on the VLAN ID. It's called the system extended ID. So here we're talking about VLAN 1. So they simply added 1 to the actual priority of 32.768. In fact, let me prove it to you. Let me just say, show me spanning tree for all the VLANs. Here is VLAN 100. So instead of 32.768, it's 32.868. You see, they just added the VLAN number of 100 to the priority of 32.768. And yeah, let's see, VLAN 200, that would be 32.968. We add 200 to the default. So that's what's going on there. But let's get back and just interrogate this first VLAN. Now, it says that Fast Ethernet 1/0/13, that is our root port. And it is forwarding down to our root, which we think is switch 2. It's 100 megalinks, so the cost, as we saw earlier, we're using that short path cost method. We are going over a 100 megalink, and it's a cost of 19. Now, we'll get into this next part in just a bit, but here is the port priority, and there's a dot, and that is the port number. More on that in just a few minutes. Now, this alternate port, it says it is blocking. Okay, why is that? Well, if you look at at each end of that link between switch 1 and 3, who has the lowest MAC address? Switch 3 does. So yeah, I'm on switch 1. My end's going to be blocking. So that is consistent with what we've seen. Let's take a look at switch 2. I'll say show spanning-tree for VLAN 1. This should be the root. That's what you told me. In fact, it tells us very clear to look at this. It says this bridge is the root. Awesome. So our MAC address is the root bridge's MAC address. And because we're the root, all interfaces coming into us are by definition designated ports. So all these are designated ports, and they're all forwarding. They're all 100 megalinks, so they all have a cost of 19. One switch to go, that is switch 3. Oh, by the way, let me point out that we do have a couple of links going between switch 2 and switch 3. I'll say show spanning-tree for VLAN 1 on switch 3. And this is interesting. All right, now, we've already said that on that link between switch 1 and 3, we said the switch 3 end is going to be the designated port, and it is. We see that right here. But I've got those two links going between switch 2 and switch 3. I'm forwarding on the bottom port, and I'm blocking, or I'm forwarding on Fast Ethernet 0/1, I should say, but I am blocking on Fast Ethernet 0/2. Why is that? Well, we said we're gonna look to see who's on the other end of this link, and it's switch 2 in this case, and we're going to say, all right, who has the lowest bid? Well, it's the same. They're both going into switch 2. Who has the lowest port ID? Well, on switch 2, it's Fast Ethernet 0/1. Okay, so that's going to be our root port, and we have to be blocking on the other one. So all that's pretty consistent with what we talked about in theory. Now, let's see how we can mix this up just a bit. I'll just stay here on switch 3, and let's say that we want to make switch 3 the root. We'll just play with VLAN 1. Just keep in mind, we can do this for each of our VLANs independently. But let's say that we want to make switch 3 the root for VLAN 1. A couple of ways we could do this. I could go into global configuration mode for switch 3 and say spanning-tree for VLAN 1. And I could say root primary or secondary. And I could make it the primary root. But let me back up. I will show you the second way of doing it. We could say, if I could spell, that would be helpful. I could say, here is your priority. Remember, we said we look to the switch that has the lowest bridge ID, and the first part of that is the priority. By the way, we have to do this in multiples of 4096. So this could be 8192, 16384, 24. Okay, I don't know that number off the top of my head. But yeah, multiples of 4096. So I could manually do it. But in fact, I think I'll do it both ways in our demo at some point today. But let's just right now say the root primary. I'm going to make it the primary root, and I'll press enter. Wonder what happened when I made switch 3 the root, because switch 2 had been the root. If I now do a show spanning-tree for VLAN 1, what's going on? Oh, look at this. We caught one of these ports in the listening state as it was transitioning through blocking, listening, learning, forwarding. We caught it in the listening state. So now, is it in the learning state? Yep, look at that. We caught it in the learning state. And after 15 seconds, we should see it forwarding. Nope, still learning. Forwarding. There we go. We're now forwarding. So now all these ports are designated ports. So we are now the root for switch 1. Now let me explain what happened when I typed in that root priority option. That said, we're going to go. Now, let me back up here. I want to show you something. I was showing you this command earlier. I said we could say root primary and root secondary. Primary is going to, that's going to make this switch into our root bridge. If I said secondary, the idea is good. It's saying, well, if our primary route goes down, we should have a secondary route. That's one of the things I had to have in my designs that I used to have to defend. I would have to say, here's the backup route. That does not work as well. You would think I could just say, this is primary, this is secondary. The logic is different, and most people aren't aware of this. I want you to know it, though, so please take notes on this. If I say route primary, which is what I did, it is going to go look to see who is the current route bridge. And it's going to say, all right, whatever that route bridge's priority is, I'm going to reduce that by either 25%, or if it's already or let's say it's the default. If it's 32,768, which is what it is in our case, we're going to reduce that by 25%. In fact, is that what happened? Let's try. Let's do a show spanning -tree for VLAN 1. Our priority is now, oh, actually, let's not add the VLAN ID. It's 24,567, or 76, excuse me. You can try this on your calculator. Take 32,768 and multiply by 0.75. 32,768 times 0.75, and you'll get 24,576. That's 25%. Let's say that the route bridge had already been manually set to this. What do we do then? It's going to say, oh, I need to go even lower. So it's going to go to the next increment lower. That's an increment of 4,096. So using the primary option is very intelligent. It's going to actually see who the route bridge is and either go down 25% or the next 4,096 multiple below whatever the current route bridge is. The second option is not as impressive. Let's go to switch SW2, and let's say, I could say spanning tree, VLAN 1. Let's make you the secondary route. Now, when I do that, let's take a look at its priority. If I say show spanning tree, it has a priority now of 28,672. What is that? That is 1/8. We reduced 32,768 by 1/8. So try it in your calculator. Take 32,768, multiply by 0.875. That's 1/8, 12.5%. And you'll get 28,672. Now here's why I say I don't like this. Here's why I'm throwing shade at this. It makes the assumption that whoever is currently the secondary must be 32,768. It doesn't check. If we had somebody go in and administratively configure earlier the route as 8,192 and the secondary as 16,384, and we came along and said, oh, no, now I want this to be the secondary. Route secondary, enter. It's not going to work because it assumes that the current secondary is 32,768, and it might not be. It doesn't check. The primary option checks. Okay, off my soapbox, rant over, but I don't trust it. I wanted to show it to you in action, but in a later demo today, I'm going to show you how the better way of doing it by actually setting the priority. It's better in my opinion anyway. But that is how we could, from a default configuration, set the primary and secondary routes. Now, let's prove something I was mentioning earlier. Here on switch SW2, if I say show spanning tree VLAN 1, you'll see that in these two ports going over to switch 3, notice I'm forwarding on the first port, but I'm blocking on the second port. And that's simply because the far end, in other words, switch 3, the far end has a lower port ID on the other end of Fast Ethernet 0/1 as opposed to Fast Ethernet 0/2. Because if you look at that topology, 0/1 on one side connects to 0/1 on the other side. And the question I asked you earlier is, if those were crossed, who's going to be my root port? And I think most of you got it right. You knew it was the lowest port ID on the far end. So what I'm going to do right now is I'm going to go over to SW3. So I need to step away from the mic for about 20 to 30 seconds. And I'm going to physically go in my server room and I'm going to swap the cables. I'm going to swap Fast Ethernet 0/1 and 0/2. I'm going to swap that on SW3. And I predict that will swap the states here on SW2, proving that it's not the local port ID, it's the remote port ID. All right, I will be back hopefully in 20 to 30 seconds. So talk amongst yourselves while I'm gone. I'll be right back. All right. Sorry for the dead air, but I have returned. I guess you could see it on screen as I was unplugging those things. Well, let's give our command again. And we still caught this in the learning stage, so we'll give it a moment. Learning. We'll transition to forwarding hopefully in just a moment. There we are. We're in forwarding. Well, look at this. We originally were blocking. Let me scroll back up. We were originally blocking, before we started this, let's see, switch to, scroll back up to the top here. Here we go. This is before the change. I said we were forwarding on Fast Ethernet 0/1, we were blocking on Fast Ethernet 0/2. And to prove that we're paying attention to the far end and not the local port ID, I swapped the cables on Fast Ethernet 0/3. And notice that these have now swapped. Now, we used to be forwarding on Fast Ethernet 0/1. Now we're blocking and we're forwarding on Fast Ethernet 0/2. So, I think that proved the point. But there is another way that we could do that without physically swapping cables. Give me another 20 seconds. I'm going to put these back to their original state, and I'm going to show you a way that we could administratively control that without physically moving cables around. So, okay, talk amongst yourselves again. I'll be right back. All right, so when I unplug those and plug those back in, let's see what our state is now. Let's give it a few seconds until we transition to forwarding and blocking. But you can see that Fast Ethernet 0/1, it's on its way to forwarding. Learning, learning. We'll get there in a moment. Forwarding. Okay, we are back to the way we were before. I put the cables back the way they originally were. However, there is another way to influence which port we're using when we have more than one connection. And that's in this column right here. This is our port priority, and this is the port number. That's what NBR stands for. It kind of looks like neighbor, but it actually means number. Well, what we can do is we can influence the priority of one of our ports. Now currently, notice that Fast Ethernet 0/1, 2, 3, they all have a priority of 128. Now you might think, what's up with the number? Why is the number 3 associated with Fast Ethernet 0/1? It's on most Cisco Catalyst switches that I've noticed, they add 2, maybe it's the uplink ports are counting, but they add 2 to whatever this last digit is. So if the last digit is a 1, add 2. I'm guessing for the uplink ports. Add 2, and it's a 3. Add port 3. Add 2, it's a 5. That's where the number comes from. We did not change the number, but we can influence the port priority, or the port cost, we could say. So what I'm going to do is I'm going to go over to, let's go over to switch 3, and I'm going to change switch 3's port priority. So again, let's do a show spanning-tree for VLAN 1. And again, the port priority for everybody is 128. And we saw that on switch 2 just now, we saw that we were blocking on Fast Ethernet 0/2 because this has a higher port cost, which is kind of a combination of the priority and the number. The number was higher here, so we were blocking on this link over on switch SW2. What I'm going to do, though, is I'm going to reduce the priority on Fast Ethernet 0/2 such that it suddenly becomes more attractive. Here's how I do that without having to move cables around. I'm going to go into, and I'm on switch 3 now, I'm going into Fast Ethernet 0/2, and I'm going to say spanning tree VLAN 1, because we can do this on a per VLAN basis. VLAN 1, I'm going to say the port priority is, and it has to be in increments of 16, I'm going to make it a 32, which is well below the default of 128. So let's make that a 32. And let's see what it looks like now. I'll say show spanning -tree for VLAN 1. And now the port priority is 32. When SW2 is looking over at this, it's going to say, which end of this has the lowest port cost? And it's going to say, they normally have the same priorities on those ports, but look this, Fast Ethernet 0/2 on my neighbor, from the perspective of SW2, the neighbor is SW3. On SW, let me go over to SW2, we're going to say my neighbor has a lower port cost on its Fast Ethernet 0/2. So I'm going to use it. Check this out. And just by changing the port priority on SW3, we've now changed which ports are blocking and forwarding. They swapped again over on SW2 without me physically swapping cables. I just changed the far end. That's the big point I was trying to make. I was changing the far end port priority on those. So I hope you enjoyed that. A lot of people really struggle with those concepts. So hopefully I shed some light on why it's great to use the primary option when setting your route. It's not a good idea to use the secondary option. We prove that it's the far end port ID that matters, and we can change not just the cables, but we can change the priorities. And that was a look at PVST Plus. And again, Cisco came in and said, whoa, let's make common spanning tree better by giving a different instance of spanning tree to different VLANs. So I configured VLAN 1. I won't do it for time's sake, but we could go into VLAN 100 and say SW1 is your route. And for VLAN 200, SW2 is your route based on traffic patterns. Let's look at the traffic flow that we see in each subnet, in each VLAN. In other words, in each broadcast domain. So I think this is a huge improvement over common spanning tree. But then the industry came along, the IEEE, and they said, okay, we get it. We get it that different VLANs might benefit from different versions of spanning or different spanning tree topologies. But what if we did this? What if we said, or what if we made the assumption that if we have a bunch of VLANs, sure, different VLANs might benefit from different topologies, but I'll bet you a lot of the VLANs would benefit from the same topology. I bet we might have several VLANs that would benefit from having, let's say, switch SW1 as the route, and another set of VLANs that would benefit from having SW2 as the route, or switch A, B, C that we see here. So enter multiple spanning trees protocol, or MSTP. Or sometimes you see this written as simply MST for multiple spanning tree protocol. It's a standard. It's IEEE 802.1s if you want to jot that down just for your notes. 802.1s. And here's the idea. We love the benefit of giving each VLAN its optimal spanning tree topology. But we realize if I've got hundreds or thousands of VLANs, which is very possible in a data center. That's one reason we instead want to use VXLANs in a data center. But in a data center, it's very possible, or even large enterprises, we could have hundreds or thousands of VLANs. Do I really want to be running hundreds or thousands of instances of spanning tree protocol? That seems like it might put a processor hit on my switch. So what can I do? Instead of saying each VLAN has its own tree, what if I create what are called spanning tree instances? Here, I'm creating two instances. And I'm saying for instance number 1, switch A is the root. For instance 2, switch B is the root. So now, instead of running an instance of spanning tree for every VLAN, I'm just running 2 instances. And I'm making the observation that VLANs 1, 2, 3, and 4, they would benefit from having a root of switch A. So I'm going to put them into instance 1. VLANs 5, 6, 7, and 8, that they would benefit from being pointing to switch B as the root. So I'll put them in instance 2. It's the best of both worlds. We're minimizing the number of spanning tree instances that we're running in order to give every VLAN an optimal tree. That's a great solution. And for years, I would tell my students, this is how I would do it. I've changed my tune a little bit just because, well, one reason is switch processing power has got just orders of magnitude more than it used to be. Today, on modern Cisco switches, I'm not concerned about running hundreds of instances of spanning tree protocol. I think that would be just fine. I would rather overcome the delay in convergence as opposed to reduce the number of instances. So even though this used to be my favorite, today my favorite is using rapid PVST, or PVST Plus if you prefer. Now, the industry has a standard, and it's called 802.1W. But before we get that, I do want to show you real quick, even though it's not my go-to today, it used to be, I want to show you how to set up multiple spanning trees protocol because it's on the blueprint for the ENCOR exam. I want you to know how to configure it. So let's go over to our topology again. We'll just use our same topology, and I'll bring up that topology, and let's configure multiple spanning trees. First, and we're on switch 2, I'll just start here. I'll say configure terminal. If I could spell, that would be super helpful. Spanning-tree MST configuration. So here is where I create my instances and I put VLANs in those instances. So let's say I'm going to have an instance of 1 that's going to contain VLANs 100, and 300. I'm going to have instance 2 that contains, I'm sorry, I said 200, I think. I meant 300. 100 and 300 in instance 1. VLAN 2 is, or instance 2 is going to contain VLAN 200. Now, by the way, I've got more VLANs than this. I've got the default VLAN of 1. I've got another VLAN on this switch of 400. I didn't assign them to anything. What did they do? Well, I want you to know, in addition to instance 1 and 2 that I created, there is an invisible instance 0 that's there. And it's like the catch-all. It's all the catch-all, or it's going to catch all of the VLANs that I did not explicitly assign to an instance. Those will be in instance 0. Okay, I've done that, and I need to do that on all of my switches. They all need to agree, so let me very quickly go to each of my other switches, and I'll just type in the same thing. So spanning-tree, MST config, and for instance 1, we're entering VLANs 100, 300, instance 2, VLAN 200. Boom, we're done there. Let's go to switch 3, do it again. I'll say spanning-tree MST configuration. For instance 1, you've got VLAN 100 and 300. Instance 2, you've got VLAN 200. Okay, we've done the same thing on all of our switches now. Let me go back to switch 1 for a moment. Let's say that we want switch 1 to be the root for instance 1. And we want it to be the secondary for instance 2. So let's do this. Let's say spanning-tree MST 1 root. Oh, you know what? I said I wanted to do it a different way here. I could say root primary and root secondary here, but I'm kind of partial to using the priority option, especially when it comes to secondary. So I'm going to statically set the priority. It's got to be in increments of 4096. So I'm going to pick as my root, I'm going to say 8,192 for instance 1. And for instance 2, I'll make it the secondary. I'll say the priority is 32.7, no, actually not 32, 16.384. Okay, that I think will make, I need to go set switch 3 to be the primary of instance 2, and then I think we'll be in good shape. So on switch 3, I'll say, okay, you're primary for 2 and you're secondary for 1. So I'll say spanning hyphen tree for instance 1, I want you to be the secondary. So I'll say your priority is 16.384. And for instance 2, actually, what did I do back here? I want to make sure I'm not. Yeah, I'm doing that right. For instance 2, I want you to be 8,192. So I'm just double checking here. Yep, that looks good to me. All right, let's do some verification. Oh, big step, almost forgot. We're still running in PVST mode. That's our default mode, or PVST plus, even though it says PVST. Check this out. If I say show, really cool command to write down, by the way, show spanning tree summary, it tells us what mode we're running in. And right now, I'm still running in PVST mode, even though it's technically PVST plus. I want to change that. I want to change that to MST for all of my switches. So let's go through all the switches really quickly, and I'll say spanning hyphen tree mode MST. Let's do the same thing for the other two. Spanning hyphen tree mode MST. And one more to go. Spanning tree mode. Oh, by the way, here are the options. Rapid PVST, which is what we're going to talk about next. The default of PVST, or what we're doing now, MST. So we're configuring all the different options today. And I can confirm that we are running MST by saying show spanning tree summary. Look at this. It says now we are in MST mode. Oh, and here are those instances. Here is instance 1. Here is instance 2. And here is instance 0. That's the catch-all that I was referring to earlier. So that is a look at how to set up multiple spanning trees protocol. Now we've got one other flavor of spanning tree that we want to talk about in theory and then configure, and that's rapid PVST. Now, by the way, the industry is not using PVST. The industry, if you're on a non-Cisco device, you may see it just called simply rapid spanning tree, or RSTP. The standard is 802.1W, by the way. But it's that's the industry standard. We're focused on rapid PVST, which means we're using 802.1W, but we're using multiple instances of it, one instance for each VLAN. And I say it's rapid, and that brings up the question, how rapid? We're going from 50 seconds down to what? It depends. If it's a direct link failure on a switch, that switch can converge in a matter of milliseconds. Or we can converge, usually it's a maximum of 6 seconds. That's 3 times the hello time, by the way, is how that's derived. But it's probably going to be somewhere between just a few milliseconds and about 6 seconds. That's a lot better than 50 seconds. So I'm a huge fan of this. And in modern switches, I do not care that we're running an instance of spanning tree for each of my VLANs. And if I'm in a data center and I'm thinking, but I got thousands of VLANs, I'm not going to be doing this anyway. I'm going to be running VXLANs. But in the enterprise, this is my go-to solution. I've got to define some terms for you. The good news is most of it is the same as what we've already talked about. Most of it is the same as PVST. And what I mean by that is we still have a root bridge. We still have root ports, which is the port on a non-root bridge that's closest to the root in terms of cost. And we still have designated ports. Those are the ports, one per segment, that that are closest to the root in terms of cost. And here we only have one segment that's not connected to the root, and it's designated on switch SW3. We still have the concept of a disabled port. You might say, why wasn't that a designated port on switch 2 over on the left? It's disabled. It's administratively shut down. Here's where it's different, because all that's the same. Here's where it's different when it comes to blocking ports, which we called also non-designated ports. Here's the difference. There are two times we might have a blocking port. One is when we have a connection between two Ethernet switches. It's a point-to-point connection, like that connection between switch 2 and switch 3. The port on switch 2 is going to be blocking, but we call it an alternate port. It's an alternate port. Now, for some reason, they paid a lot of attention to how we would handle Ethernet hubs. I hope you're not using Ethernet hubs in your topology today. But if you are, and you're going up from switch 3, sorry, hit the microphone there. You're going up from switch 3 and then back down to switch 3. You might say, those are two segments. Shouldn't we have a designated port on? No, that's one segment. If you're going through a hub, that entire loop is one segment. So that's also going to be blocking. But it's going to be a different kind of blocking. It's going to be called a backup port instead of an alternate port. So that's the subtle difference with rapid spanning tree versus our traditional spanning tree. And the roles are a little bit different as well. Instead of saying blocking, we say we are discarding. We do not go through the listening stage. We go directly to the learning stage, and then we transition to forwarding. And one way this can happen so quickly is that when something happens in this topology, the switches are proactively educating one another. Here's a term for your notes. When there is a change in the network, that's called, one switch can notice that. It's kind of like, I don't know if you have it where you live, but have you heard of the neighborhood watch program? That's where all the neighbors in a community, they're keeping an eye on something and they'll alert one another if something's happening. Well, that's what rapid spanning tree does. Each switch is capable of sending a topology change notification to educate its neighbors about this change that just happened. We don't have to wait for the absence of BPDUs from the root bridge for 20 seconds. We can proactively educate one another. And I'm going to go through that education process with you in just a few moments, but just a few more terms first. I want you to know that a link between two different Ethernet switches, those are going to be called point-to-point ports. No surprise, they literally are point-to-point ports. And the port connecting out to a laptop, that's going to be called an edge port. But you might think, hold on, how do we know it's a point-to-point port versus an edge port? For your notes, here's the definition. A point-to-point port is when we have full duplex running on an interface. We're assuming if we're interconnecting two switches, those are going to be full duplex connections. But isn't it a full duplex connection going to my laptop as well? Yeah, it probably is. So technically, yes, that connection to the laptop, it is a point-to-point link, but it's a special type of point-to-point link called an edge port. Remember that 30-second delay I was talking about when we plug a brand new device into an unused switch port? I don't want to go through that delay. So by making this an edge port, it makes me go active, bam, almost immediately. We are giving our solemn vow to that switch port that I promise I'm not going to cause a loop. I'm not going to plug a switch into you. You will never see a BPDU coming in on that port. We're going to do that with the feature we're going to talk about after our next break called Port Fast. But again, they're considering that Ethernet hub up there. And that Ethernet hub, we're going to call that a shared link. How does the link come to be known as a shared link? Half duplex. Because remember, an Ethernet hub cannot use full duplex. It can only transmit or receive at any one time, not at the same time. So if it's shared, we assume it's connecting to a hub. Or if it's half duplex, we assume it's shared and connecting to a hub. Now, here's how we educate one another. This is really cool. You might want to take some notes on this. Let's say, and now I'm just showing you a small, we've just zoomed in on one little part of a bigger topology. I'm just showing you when a change occurs, how one switch, using those topology change notifications, how one switch is going to very quickly educate its neighbor that, hey, things are different. The root bridge is now this way. So at the beginning, the root bridge used to live somewhere off the bottom of the screen. We don't even see it right now. It was somewhere down below. This is a large topology. We're just zoomed in on these two switches. It used to be somewhere down there, and now something bad happened, and now the root bridge is the switch with the best bridge ID. It's somewhere up at the top of the screen. So switch 1 sees that. Maybe it's directly connected to it. Maybe it learned it from an upstream neighbor, but somehow switch 1 learns that. And its port on the top used to be a designated port. Suddenly, that's the port that's closest to the root in terms of cost. That should not be a designated port. That should be a root port. So let me walk you through this step by step. I've numbered them to help you keep them straight for your notes. Step 1 is switch 1 is going to transition that designated port into a root port, because now that is the port on that switch that's closest to the root in terms of cost. So we've transitioned it to a root port, but we got a problem. The bottom port on switch 1 is also a root port. We don't want to get into a weird looping thing where we're making our tree unstable. So just for safety, temporarily, as step 2, we're going to temporarily block that bottom port. Now, just because we're blocking and not carrying user data, that does not mean we cannot send out BPDUs to our neighbors. So we're going to do that. We're going to try to tell switch SW2 and convince them that, hey, the root bridge is now up, not down. So we send what is called a proposal message down to switch 2. And we say, hey, I'm proposing that you come to me if you want to get to the root. I know right now on our link that we share, you're claiming to be closest to the root. You've got the designated port in this segment. I'm proposing that maybe I should be the designated port because I'm closer to the root. And to prove it, here's the BPDUs that I just received. Check out this bid. Obviously, that's the best bridge ID. You need to come to me. And if switch 2 believes that and it says, what do you know? That really is the best bridge ID. I guess I need to start going up to get to the root. To do that, it's going to change its designated port to a root port, because now that is the port on switch 2 that's closest to the root in terms of cost, and it's going to go up. It needs to let switch 1 know that, okay, you sold me, you convinced me. So it sends an agreement. That's step 5. When switch 1 gets that agreement, good. They believe me, so now they've changed to being a root port. It's safe for me to come out of a blocking state on my bottom port and transition into a designated port. Those are the 6 steps of that quick convergence. And then, I won't go through all 6 steps again, but it just kind of carries on. Switch 2, it's going to block its bottom port, send a proposal to its neighbor somewhere off screen, and the process happens over and over again. That's one way that we can educate our neighbors very, very rapidly about changes that are happening in the topology. Let me show you how to set this up. And the great news is the configuration is almost identical. A lot of it is identical to what we did with PVST Plus. Now, first, let's see, we're on switch 1. Remember right now, if I say show spanning tree summary, we are currently running in MST mode. And it reminds us, this is an IEEE standard, 802.1s specifically. Well, we need to change the mode to rapid PVST. So let's do that first. Let's go to all of our switches and I'll say spanning tree mode. And remember, we can say rapid, not PVST plus, but just rapid PVST. Let's do that on all 3 switches. Spanning tree mode, rapid PVST. 1 switch to go. Let's go to switch 3. And I'll say spanning tree mode, rapid. Oh, already did the tab autocomplete. So I think we're in good shape. I think we're in good shape on all of these switches. We're currently running rapid PVST plus. We can confirm that with a show spanning tree summary command. Yep, we're currently in rapid PVST mode. Awesome. Let's say that I want to make switch 3 the primary for VLAN 1 and the secondary, we'll say, for VLAN for VLANs 100 and 300. Let's use a mixture this time because we can use these different approaches together. I'm going to say spanning-tree VLAN for VLAN 200. I want to be the root, and I'm going to say primary. Now I am totally comfortable saying primary there because I know it's going to go out and see who what the priority is for the current root, and it's going to make sure that we beat it. So I'm not worried about putting in a number there. But I am a little concerned about putting in a number for the secondary because it doesn't do that. It just says, I bet they were 32,768. Let me reduce myself by 12.5%. So I'm going to put in a number there because I don't trust that. I'll say spanning-tree VLAN 100 and also 300. I'll say I want my priority to be, let's see, trying to do the math in my head here. Let's go to 24,576. I think that's a multiple. I just want to make sure here. Let's say show spanning tree. So for VLAN 100, I'm 24,560. Now, I think I said it the same for both, didn't I? Yeah, I need to change that. Let me make it a higher value. I've got to break out the calculator here. Let's see. I'll bring up my calculator in this blank window and we can do it together. Let's say it's got to be in multiples of 4,096. So I'll say 4,096 multiplied by 7 is, 28,767. Let's set it to that. So I'll say, or actually 28,672. So let's say 28,672. That's good. That'll work. That'll make it the secondary. And then, if I say show spanning-tree, we should be the root for VLAN 200. And it says, yep, this bridge is the root. I'm also the root for VLAN 100. That's simply because I've not gone to I've not gone into switch 1 and set that up. So let's do that really quick. Let's go to switch 1, and I'll say spanning tree. I want you to be the secondary. I want you to be the secondary for VLAN 200, and that's going to be what value? 68,672. Priority 8,672. And I want you to be the root for VLANs 100 and 300. And I'll just say root primary for that. And if I say show spanning-tree, it should show that I am the root for VLAN 100. Yep, we are the root. I should not be the root for VLAN 200, and I'm not. The root starts with 0014. Looking at our topology, yep, that is switch 3. So that worked as expected. But let's zoom in on one of those VLANs and take a look at those different types of links that we have. Let's say show spanning tree VLAN. Let's take a look at 300 as an example. Here, I've got designated ports because I'm the root for VLAN 300. So all my ports are designated ports. No surprise there. Let's go to, let's go to switch 3. I'll say show spanning tree for VLAN 300. Okay, and it just so happens that I do happen to be forwarding on all those, and that's because I've got a lower MAC address, it looks like, than SW2. But I want to take a look at this. I want to change those link types we talked about. If I want to set a link to, let me go into a port that I'm not using. I'm not using 1/0/1. Let's say I wanted to set the link type, spanning tree link type, and use context-sensitive help. We talked about point-to-point and shared, but I said there was a special type of point-to-point called an edge port. How do I make something into an edge port? I've got to turn on a feature called port fast. So let's pretend, and we'll talk about this after our break, by the way, but let's pretend that Fast Ethernet 1/0/1 is connected to a PC. I don't want to wait for 30 seconds for that thing to come up. So I want to speed that process up. I'm going to say spanning-tree port fast, and I'll press enter. And it gives us a caution about this. It said we should only enable this going to a single host. If you connect this to a switch, you're setting yourself up for a disaster. You're going to have a broadcast storm possibly. All the disclaimers are happening here. But if we know that we're only going to plug a PC in here, we should be all good. But that's how you make it into an edge port. Now, there's nothing connected to it right now to show it to us, but that's how you make something into an edge port. And that is a look at the configuration of rapid PVST. Hey, welcome back from the break, everybody. And during our last section here in today's webcast, we're going to talk about some performance enhancements for spanning tree protocol. Specifically, two things. We want to see how to decrease convergence time, and if we're not using something like rapid PVST plus, that is, and how to increase the stability of our network. There are 7 different tools I want to teach you right now. They are, first up is PortFast, which we've already talked about. We'll review that again and show you a different way of configuring it. But PortFast is one. Another one is uplink fast and backbone fast. Now make a note, if you're using rapid spanning tree or rapid PVST plus, you want to use PortFast, but you don't want to use uplink or backbone fast because you don't need those two with rapid PVST. You could still use those with MST or just regular PVST or CST if you're using a vendor that supports that. But first of all, PortFast. PortFast, we said, is going to make a solemn vow to a switch port to say, I promise I will never send you a BPDU. You're never going to form a loop by negating your spanning tree process with me. Please just let me go active already and not have to wait for 30 seconds. So by doing that, the switch will say, okay, I trust you. I hope you didn't lie to me. And it lets that port go active almost immediately. But we plug in, for example, this laptop into switch 4 on gig 0/2, and we say, for that port, we want to make it a port fast port. And we could do that on a port by port basis, or we could enable it globally on a switch. You might think, how could we enable it globally? How do we have the knowledge of which port is going to be forwarding, or which port is going to be connected to an in station versus which port is connected to a switch? Well, there's a design assumption that we're making here. And that design assumption is that if I have a link between two switches, it's a trunk. Now, there are exceptions, so don't do it globally if you have that exception. But in general, when we're interconnecting switches, we're going to be sending traffic from multiple VLANs across that connection. So we want that to be a trunk connection. So if you enable this globally, it's going to turn on PortFast for every port that's not trunking. Every active port that's not trunking, it assumes, oh, they must be connected to in stations. So you can do it on a port by port basis, or you can do it globally, and it's going to make that station go active almost immediately. Now, I already showed you how to do this for on a port by port basis. You simply go into interface configuration mode, and you say spanning-tree port fast. But if you want to turn it on globally, in global configuration mode, you say spanning-tree port fast default, if you want to jot that in your notes. That is going to say turn on port fast for every non-trunking port that's up. All right, let's take another look. Let's take a look at something else that can help reduce convergence time. This is great if you're doing PVST plus. Again, or MST, you don't need it if you're using rapid PVST. So skip it for that. But it's called uplink fast, and it helps us with a direct link failure. Now, in this topology, notice that I've got a laptop at the bottom of the screen, and we're pretending it has a MAC address of all A's. And we're typically going to use this uplink fast feature on access layer switches. And we don't turn it on for a specific port, we turn it on for the entire switch. And it's going to react to a direct link failure. You see, here's the port states on SW4. Pay careful attention to this. SW4 has a root port going up to SW2. That's where traffic is currently flowing. It's got a blocking port going over to SW3. That will be a backup port if that primary port, if that root port were to fail. Okay, let's say that port failed. Okay, now gig 0/3 transitions, I sped it up, but after 50 seconds it transitions to a root port. But we've got a problem. Switch 2 in its, switch 2 in its routing table or its MAC address table, it thinks that the way to get to the all A's MAC address is to go at gig 0/1. Well, that's broken. Switch 3 thinks to get to the all A's MAC address, it needs to go over to switch 2. That's no longer going to work. Switch 1 thinks to get to the all A's MAC address, it needs to go down to switch 2. That doesn't work. We've got incorrect MAC address tables on all of these switches about how to reach that MAC address. And I'm just showing you one laptop, but there could be hundreds of laptops. Here's what switch 4 is going to do. It's going to say, I've got this MAC address table for all these directly connected MAC addresses, and I just switched over to another port. I bet everybody's still going to be trying to come to me on this port that's no longer active. What can I do to fix that? What I can do, this is a Cisco proprietary solution, by the way. What I can do is I'm going to send out a bunch of, some people call them dummy MAC address, or dummy multicast frames, going to a multicast address, a layer 2 multicast address that Cisco has. All the switches belong to this multicast group at layer 2. So I'm going to send up, for example, a multicast frame. The source port is the all A's MAC address. That's my laptop. But notice the destination, 0100.0CCDCDCD. That's a multicast MAC address that Cisco owns. That's the Cisco vendor code, and all switches belong to that multicast group. So when switch 3 gets that, it's going to send it out to all the other switches. And notice who the source address was. It was the all A's MAC address. So switch 3 just learned that the all A's MAC address now comes in through gig 0/1. Switch 2 just learned that to get to the all A's MAC address, it needs to go over to switch 3. Switch 1 just learned to get to the all A's MAC address, I need to go down to switch 3. So because we had that direct link failure, almost immediately, switch 4 starts firing out those dummy multicast frames to educate the topology where those MAC addresses really live. That's for a direct link failure. We also have, here's how to configure it, by the way. We can set it up globally on the switch. We don't set it up on a port-by-port basis just by saying spanning-tree uplink fast. It's that easy. Now, let's take a look at backbone fast, which is going to help us recover from an indirect link failure. Here, switch 1 is the root. Switch 2 points up to switch 1 on gig 0/3. Switch 3 points up to gig 1 on 0/3. And there's that link between switch 2 and 3 at the bottom. The switch 3 side is blocking. And here, we're going to configure this on all of the switches in our topology, and we enable it globally again. This is not a port-by-port thing. We globally turn it on all of our switches. And it's going to react to a indirect link failure. Here's what I mean. Right now, SW2 is just merely sending along frames up to SW1 over that link, but it broke. Switch 2, enable for backbone fast, says, I just lost connectivity with my root. Maybe I'm the root now. It has delusions of grandeur when configured for backbone fast. It thinks, I feel like I might be the root. I'm gonna usurp the throne. I'm gonna start telling everybody that I'm the root. Come to me. So it's going to advertise, switch 2 is going to advertise over to switch 3. Hey, guess what? The root is down. So now, I am the root. And it sends it what we're calling an inferior BPDU. I say it's inferior because switch 2's bid, its bridge ID, is higher. In other words, less attractive than switch 1's BPDU. But switch 2 is not thinking about that right now. It says, I lost connectivity with the root bridge. I'm going to take over. And it sends it to switch 3. And switch 3 says, What? Are you sure? I'll be right back, Switch 3 says. And Switch 3 says, I could have sworn SW1 was the root. So it's going to send a query up to SW1. It's called a root link query, an RLQ, saying, I got this guy over here. They're claiming to be the root. I could have sworn you were the... Are you still the root? I mean, here's their bid. What's yours? I think... Are you still the root? And Switch 1 gets that and says, oh, Switch 2's up to it again. Yeah, I'm still the root. It sends a reply. It's called an RLR, a root link reply, saying, yes, here's the proof. Here's my bid. I'm still the root. And Switch 3 tries to gently tell Switch 2, I know you had your sights set on being the root, but take a look at this. This is a superior BPDU that I just got from Switch 1. I think they should be the root. And Switch 2 says, how embarrassing. You're right. Okay, I'm not going to be the root. I'll just forward my traffic to you. So that's how Backbone Fast works. We enable it globally, and we simply say in global configuration mode, spanning -tree Backbone Fast. Now, let's talk about 4 features that some can be dangerous, but they can increase the stability of our spanning tree topology. And they are BPDU guard, BPDU filter, and there's root guard and loop guard. Let's take a look at each one of those. Beginning with BPDU guard. And we probably want to enable this on ports that are already configured for port fast. So if we give a port fast configuration on a port, but then somebody comes along and maliciously or even accidentally connects an Ethernet switch into that port, what happens? Well, as soon as we see that first BPDU coming from that switch, we're going to say, oh, we've been lied to. I'm going to administratively, I'm going to bring this port down. I'm going to go into what's called an error disabled state. I'm not going to be passing traffic because I'm now receiving BPDUs on a port that you promised me I would never receive a BPDU on. So I know I should not be in port fast mode. You need to go fix that problem before I forward any more traffic. Yeah. Now, that's not to say that port fast would not do something similar. If we started sending BPDUs into a port configured with port fast, it would eventually catch on that, whoa, I think we got a loop going on here. Let's shut this down. But we don't even want the most temporary of loops being set up. We want to stop it in its tracks. The very first BPDU to come into that port, we want to say, nope, denied. We're going into the error disable state because we have received this BPDU. So let's say that we connect switch SW5 into SW4's gig 0/2 port, which was configured for port fast earlier when we had that PC plugged in, and it sends it a BPDU. And switch 4 says, I've been lied to. So I'm going to go into an error disable state. Here's how to set that up, by the way. We can go in to an interface and enable it on a specific interface for which port fast is enabled, or we can do it globally. We could say spanning tree port fast BPDU guard default, and it'll turn on all the ports that are enabled for port fast. BPDU filter, I even hesitate to bring up because it can be dangerous. It's literally going to filter out BPDUs being sent out a specific switch port. That could be dangerous. That could lead to a loop. Why would you want to do this? One reason is maybe you've got a couple of companies that merged. You've got Autonomous System A talking to Autonomous System B, and suddenly we're linking together their switch topologies. Maybe we don't want to be exchanging BPDUs with one another. We don't want to confuse things. We're using different timers. We have different settings. We don't want to send them information about our spanning tree, and we don't want to get information about their spanning tree. So we can say, don't send a BPDU when you're connecting to this switch in this other autonomous system. And we can enable this on a port-by-port basis, or just as another safeguard, we could say if a port is enabled for port fast, we're not going to send one of these out because a PC wouldn't need to receive it anyway. In fact, that reminds me, there was a big troubleshooting issue that I used to have when I was a network manager at a university. This was way back in time. I think... Mac OS now is, I think it's a Big Sur, which is like 11.3 something. I think we might be at 11.3 or something like that now. But way back in the day, it was with Mac OS version 7, if anybody goes back that far. I remember when Mac OS version 7 came out, if you plug that into a switch port that sent out BPDUs, it would lock it up. Or it would crash your Mac OS 7 computer. That was a little bug in the software. So I had to go into switches and do what we're talking about here. I had to turn off BPDUs coming out of switch ports. But normally, you're not going to have that issue. Normally, it's you just don't want somebody else that might have mismatched STP parameters to get confused. Please only use this when necessary, because you're setting yourself up for a potential problem. Because you're not educating your neighbors. They may think, oh, you're a safe path to get to where I want to go, when really you're not. You can cause a loop. So it is most dangerous when we enable this at the port level instead of globally, because at the port level, we might accidentally enable it on a port that's a trunk. At the global level, at least we're only turning it on ports that have port fast enabled. But here's the way it would work. Let's say that we put a BPDU filter on switch 3 going down to autonomous system B, and we put a filter on switch SW4 going up to autonomous system A. And switch 3 tried to send a BPDU down out of its port, bam, it's going to be blocked because we have a BPDU filter enabled. Again, it's most dangerous if you do this at the port level, but if you want to, if you're feeling brave, if you're feeling lucky, you can go into an interface and say spanning-tree BPDU filter enable. Or if you want to do it globally, you can say spanning-tree port fast BPDU filter default. And that will just turn it on ports that have been configured for port fast. Next up is root guard. And this could protect us against an accidental or a malicious attempt for some switch to try to take over the root role. Now, this is a serious security issue. Picture this. Let's say that I'm a malicious hacker. Now, not all hackers are malicious. I realize that's why I said a malicious hacker. But I'm a bad actor on the network, and I want to capture traffic. What I might do, there's different ways to do this, but I could launch a man-in-the-middle attack. One way I could do that is get access to a wiring closet, and I could bring my own switch. And I could plug one port into one switch in the wiring closet, another port into another switch in the wiring closet, and I could configure my priority to be something just crazy low, like 4096. So I've got a very attractive bridge ID, better than whoever the current root is. I'm trying to convince this topology to make me the root. That means I'm going to be getting lots and lots of traffic come into my switch. Then I'm going to set up span. Switch port analyzer. That allows me to make a copy of traffic appearing on one port and send it out another port. Guess what's connected to that other port? My packet sniffer. So I can capture all this traffic that I'm forcing to come to me. We want to prevent that, and we can prevent that with root guard. With root guard, we're going to configure that on ports off of which we do not expect to see a superior BPDU. We know that switch 1, we've designated it as the primary route. Switch 2 is designated as the secondary route. So yeah, I wouldn't mind if they received superior BPDUs from one another, but downstream, there should be nobody down there that's going to have a superior BPDU. But let's say accidentally or maliciously, somebody adds SW3 to the mix, and they have reduced their priority to something just crazy low. And if they send a superior BPDU, let's say into switch SW1, switch SW1 says, hold on, I've got root guard enabled. I was told ahead of time that I should never expect a superior BPDU coming in on gig 0/2. So I don't trust you. And as a result, I'm going to go into a state called a root inconsistent state. And we're going to remain that way until we stop receiving those superior BPDUs. The way you set that up, by the way, you set it up on an interface by interface basis. You go into the interface and you say spanning-tree guard root. And that is a security recommendation, and I normally would want to turn that on in an enterprise network. There's another feature I might want to turn on that kind of goes hand in hand with root guard, and it's called loop guard. Now, loop guard is going to help us again. I mentioned at the beginning of class today that I was kind of nervous. I looked out the window before class began, and there's guys out there digging near the fiber optic cable that's feeding the studio here. And if they hit that fiber optic cable, I was afraid that I might go off the air. But I think I'm still on. So we've been lucky so far, knock on wood. But let's say that we did have some sort of a damage to maybe a fiber optic cable, and we were transmitting in one direction but not the other direction. Maybe one of our two strands in a fiber optic pair was compromised. For example, when I used to work at the university, we literally called it backhoe fade, because a backhoe would come in, it would start digging, and invariably it would hit one of our fiber optic cables. Let's say it damaged one of the strands but not the other one. That could result in a situation where, let's say I'm on switch 2, I'm not receiving BPDUs on one port, but I'm transmitting BPDUs. Well, on the other end, on switch 3, I'm receiving those transmitted BPDUs coming from switch 2, but I'm not able to send BPDUs back because that half of the communication's broken. So that might lead switch 3 to think switch 2 is a possible redundant link that I could use. If my root port goes down, I could switch over to pointing to switch 2 because I'm getting BPDUs from switch 2. Seems like a good alternative. If I did switch over and started forwarding frames from 3 up to 2, I'm doing it over a damaged link where one of the two fibers have been severed. That's not going to work. To prevent that from happening, the recommendation is you enable this. You could enable it on a port-by-port basis, or you might want to enable it globally. If you enable it globally, it applies to all of your ports. And I say globally, you're probably going to do this on your distribution layer switches and your core layer switches, not so much at the access layer, but you're going to enable it globally, and that's going to turn it on all of your ports that have not already been configured for root guard. And so what happens is we say, hey, I'm no longer receiving BPDUs. I'm going to go into a loop inconsistent state until I start receiving BPDUs. And the way you set that up on a port-by-port basis is to go into that port and say spanning-tree guard loop, or you could say globally spanning-tree loop guard default. And that's going to apply to all ports that are not already configured for root guard. So you want to configure root guard first, and then you follow that up with loop guard. All right, those are 7 spanning tree enhancement features, and we're going to wrap it up with some Q&A right now.